Hello everyone, my name is João Paulo Alcântara, and today I'll be talking about the fish school search algorithm for constraint optimization. Here's the agenda for the presentation. First, I'll introduce the motivation for this work, then a brief explanation about the weight-based fish school search algorithm. Next, I'll talk about the restrict version of fish school search. Then I'll show the experiments that were carried out to evaluate the proposed algorithm and what we could conclude from the experiments and future work. Optimization problems are very common in industry environments like machinery parameterization and assets allocation. So these type of problems can be tackled by heuristics techniques. And like most real-world problems, industry matters often involve optimization with restrictions to meet the problem's requirements. So constraint handling techniques must be incorporated to algorithms before tackling these problems. Replacing experienced industry specialists as decision makers for AI systems is an obstacle for the use of optimization algorithms on industrial environments, as heuristics can return a set of parameter values from an optimization problem very different from the usual values defined by specialists. So in this scenario, niching algorithms along with constraint handling techniques are more likely to be accepted by industry managers. Weight-based fish school search is a swarm intelligence niching algorithm based on the gregarious behavior of fishes when searching for food, which uses the weight of the fish as a measure of success throughout the search. And no parameters are required to define the number of niches, and it has a mechanism to automatic balance between exploration and exploitation. Weight-based fish school search is the niching version of fish school search to tackle multimodal problems. It has four main operators: the individual movement, which is a random displacement performed by each fish individually; the feeding operator that updates fish weight according to fitness improvement during the individual movement; the link formator, responsible for splitting the school into subswarms and defining a leader to each one of them; and the collective movements. First, the instinctive movement that directs the fishes towards their subswarm center of mass, and the volitive movement that is responsible for automatically switching between exploration and exploitation. So now we're gonna move on to the restricted weight-based fish school search. The restricted weight-based fish school search divides the search process into two phases, where either a fitness function or a constraint violation is optimized. Phase 1 optimizes constraint violation function to enhance exploration and find many feasible regions, while phase 2 optimizes fitness function to exploit feasible regions in terms of fitness. And the decision of which function to optimize is chosen to be done according to the feasible individual's proportion with relation to the whole population. Here we have its pseudocode. First, we initialize user parameters, initialize fish position randomly, and while a stopping condition is not met, we calculate fitness and constraint violation for each fish, and if more than half of the population is feasible, then we define fitness as objective function. Otherwise, we define the constraint violation as objective function. Then we run the individual movement operator, the feeding operator. We split the swarm and define the leaders on the link formator. Then we run the collective movements. To evaluate the proposed algorithm, a set of real-world constraint optimization problems defined at the Congress on Evolutionary Computation 2020, containing various feasible regions, have been solved. Problems features are shown on this table. For each problem, the algorithm runs 25 times and the following metrics are evaluated. First, the feasibility rate, which is the ratio between the number of runs in which at least one feasible solution is attained within maximum fitness valuations and total runs. The mean constraint violation, which is the sum of all constraint functions divided by the total number of constraints, and the best fitness. Here we have the results for the chosen problems. We have compared the restricted weight-based Fishkill search algorithm with two of the top 5 ranked algorithms of the Congress on Evolutionary Computation 2020 competition. From this table, we can see that both competitors we chose managed to achieve 100% of feasibility rate and found the best fitness feasible for every selected problem. The restricted Fishkill search achieved the same results only for functions 4, 8, 9, and 12. On function 15, it got 100% of feasibility rate. However, it failed to find the best feasible fitness, and on functions 1 and 2, it could not find feasible individuals at all. Despite not providing feasible solutions for functions 1 and 2, Figure 4 shows that restricted Fishkill search can achieve regions with lower constraint violation values on fewer iterations compared to the algorithm and mode, making it suitable for problems with flexible constraints and that requires fewer fitness function calls. Now we get to the conclusion. So the results show that the restricted version of Fishkill search can handle some reasonable constraint search spaces and achieve results comparable to two of the CEC 2020 top ranked algorithms on constraint optimization. The restricted version of Fishkill search calculates the fitness twice at each iteration, and as the number of iterations for the CEC competition is determined by the maximum number of fitness calls, the restricted version of Fishkill search runs half the iteration compared to its competitors. This contributes to the results observed on functions 1 and 2, since the search space is very restricted due to the presence of a large number of equality constraints. The restricted version of Fishkill search also struggles to converge on problems with hardly constrained search spaces due to the randomness present on the link formator, which can keep the school from finding or remaining inside feasible regions. And in future works, we propose improvements in the restricted version of Fishkill search to include adjustments on the subswarm's link formation to avoid that unfeasible fishes drag the subswarms to unfeasible regions, and the implementation of a strategy to tackle equality constraints gradually. So that's it. Thank you very much.